All right, in this chapter, we're going to talk about a thing called variability. And variability and standard deviation are going to continue to be numbers and calculations that crop up over and over and over again as our calculations become more complicated and more complex. Because this idea of variability is fundamental to statistics. Remember, part of statistics is to describe what a set of data looks like and to be able to use that to then predict and infer meaning from that. And so variability is a good place to start, because basically what variability is how spread apart our data set is. Do we have a bunch of numbers that are clumped really, really closely together, making any one of them a pretty good representation of the entire group? Or are they spread out, meaning that we're going to have to work a little harder to kind of find a good way to describe our group in entirety than just sort of taking the score in the middle, that mean. So variability helps us describe how accurate that mean is as a representative number for the whole. And it also might then tell us that we want to use a different measure of central tendency, like the median or the mode, depending on how great the variability is in our data set. So we're going to look at some ways of defining this and describing this. So, basically, like I said, variability is how close together or how far apart scores are in a set, or how alike or not alike scores are with each other. And so some things can be relatively tight and some things can be relatively spread out. If you look at the two distributions here at the top, one is height, and we're talking about smaller numbers with height. And so the scores are kind of packed closely together, kind of making a really tight description of, everybody's height's kind of pretty close around the center. Versus weight, there's a much bigger range of numbers to deal with. So example A would be relatively low variability, or low amounts of differences among the scores. And B would be relatively high variability, high differences between the scores. So basically this does two things for us. It describes our distribution. So is it tall and skinny like in A, or shorter and spread out like in B? It also tells me how well an individual score represents everybody else. So in the height, an individual score, anywhere in that distribution is reasonably representative, but for weight, that's not necessarily going to be the case. So let's look at three different types. Range, variance, and standard deviation. And variance and standard deviation are actually just two parts of a whole that kind of go together. So let's look at the first one. Range. Range is the easiest and the least used because it really doesn't tell us a whole lot. It just tells us what the difference between the high and the low score is. So generally, to calculate the range, we just take the big score, subtract the little score. That answer is the total range. Now, you can also take this and add 1 to it. And that not only tells you how far apart the scores are, but how many possible scores there are in your distribution. And when we looked at grouped frequency tables, and those groups, you couldn't just subtract the high number from the low number and say there are that many scores. You had to add 1, right? For example, a group frequency from 90 to 94. Remember that was at the top of one of our frequency distribution tables. Maximum minus minimum would say there's a range of 4 in that frequency group. But in fact, there are 5 numbers in there, right? 90, 91, 92, 93, and 94. So max minus minimum, or max minus minimum plus 1 are both ways to describe the range depending on what I'm trying to do. All right, so that's that. Now I told you that variance and standard deviation are two parts of a whole. And the reason for that is in order to find variance, in order to see how far scores are spread apart, we have to do a little bit of mathematical manipulation. And the reason for that is our definition of variance is the average distance any given score is from the mean. But because scores spread out, remember the mean is in the middle, and so scores spread out pretty evenly, scores below the mean versus scores above the mean. If we were just to add those up, we would always get 0. So to account for this, we, instead of just subtracting those and adding it up, we're going to subtract each score from the mean and then square it to get rid of those negatives, to get rid of that zero-sum game. And then that's going to give us what we call the average squared distance from the mean, which is what our variance is, which means the actual distance number is kind of inflated, right? Because it's not the average distance, but instead it's the average squared difference, so it's exponentially larger. So using variance as a descriptor by itself doesn't give us a real accurate picture. So to get that, we're going to take that number that we get for variance, and we're going to take the square root of that and get what we call the standard deviation, which is the average distance, all right? So instead, we unsquare it, in other words. So we got to square it to get an actual distance positive number, and then we unsquare it in standard deviation in order to get the actual average distance. So it's sort of a two-step process to get us to this place. So another way to write this, and the symbol for standard deviation is this Greek letter sigma. And you can see up here we have sigma squared is the variance, or the average squared distance. So sigma can be thought of as the square root of sigma squared, because that's exactly what we're doing. You see that we have this little formula that we're going to explain in a minute. And here it is under the square root again to get to standard deviation. So these two are linked together, and you can get to either one from the other. If you have standard deviation and you want variance, you just square it. If you have variance and you want standard deviation, you take the square root. Okay, so those are our three types. And so we're not going to belabor on the range too much anymore. We're going to hit a few more ideas on that. And then we're going to move forward into the calculation process for variance and standard deviation, because there's several ways you can approach this depending on what kind of information you have. And so we're going to look at some. All right, so range, remember we said that's how far apart your scores are from beginning to end. It's handy, like we said, for frequency distribution tables and things like that, but it's basically pretty crude, and it doesn't tell us a whole lot, particularly if we have a group with, you know, outliers, some like really big scores. So example, if I give a test 1, somebody doesn't take it, so they get a 0, and then a bunch of you do take it, and you make like an 80, an 82, 88, another 88, and somebody makes a 100. Great. Well, my range, maximum, minus my minimum, my range is 100, which means there's a 100-point difference between my scores. But if I get rid of that outlier at the bottom, my range changes a lot, right? 100 minus 80. That would be just 20. So using the actual range really isn't always a good way to describe what a set of numbers looks like. So we're not going to use that just very often. All right, so let's look at the two that we are. Variance and standard deviation. Now, there are lots of ways to write out this formula depending on if you want to take it all in one big step or if you want to take it in several steps. Most of my students like to take it in several steps, and here's what those two steps are. Now, right now we're going to deal with if we have a population. Remember, we talked about the difference between a population and a sample. And these formulas are going to change just slightly for a sample to adjust for the fact that a sample doesn't completely describe everything in our population. So starting with population, variance, remember we said sigma squared is the symbol for variance for behavioral statistics. This top part here is what is known as the sum of squares or sum of squared deviations. And that's where that sort of math manipulation comes in. That's where we square all those distances from the mean to get a positive distance number for variability. And then the bottom here, we're going to divide by the number of scores in our population. And then because standard deviation is just the square root of variance, this is just a big, fancy, scary way of saying this. All right, so typically what we're going to do is we're going to calculate our sum of squares first, which will give us this. Sum of squares represented by SS over N, which is a lot less scary. So we're going to calculate that top first, put that in our formula, put our N, and then go from there. All right, so that's kind of a quick overview of how we're going to do that. So let's look at sum of squares and what the sum of squares is. Now there's two different formulas. The first formula here, called the definitional formula, that basically describes by definition what you are doing to create this squared deviation. And so in the example here, it's kind of showing you what's happening. If I have a score of 1, and this particular sample, this particular population, has a mean or a mu of 2, then if I take that score and I subtract the mean, I'm going to get these answers. So 1 minus 2 is negative 1. 0 minus 2 is negative 2. 6 minus 2 is 4. 1 minus 2 is negative 1. And so here's where the squares come in, why the squares come in. If you add up all of these deviations, all right, all of these distances from the mean, they total 0. Because by definition, the mean is the score in the center of all of the scores. So when you just subtract from the mean, you can't get anything but 0. So to accommodate for this, we take this deviation and we square it, which is where that term squared deviation comes from. And when we then add all those up, right, because you see here, this goes here, and we have our sigma. Sigma means add them all up. And this is a capital sigma, not to confuse you with the lowercase sigma. That is the symbol for variance. It's great, isn't it? Then we add up all those squared deviations. That gives us a total variance, all right? Now, that is going to get tedious when we have 100 or 200 or 1,000 subjects. So most of the time what we're going to use is this one, the computational formula. And it's just a more simple way to do the math. And here's how this reads. We first have the total of all of x squared. Now remember, this is an instruction, and it's not a mathematical fact. It's an instruction. It tells you what to do. It says add up x squared. So in order to do that, you first have to square your x, then add them up. Now this is where order of operations matters, because we're going to take that, and from that we're going to subtract a fraction. the top of our fraction is now sigma x in parentheses squared. Now remember, parentheses first, exponents second. So we had no parentheses in the first one, so we just squared them and added them up. This time we do. Inside the parentheses are the instructions, add up x. So the first thing we're going to do is add up x. And then we're going to put that into those parentheses and square the result of adding x. And then we're going to put it over n, which is the number in our sample. So for this one, it shows you here, it puts 38, sigma x squared was 38, so it puts 38 in there. It takes our sigma x 8 and puts it inside those parentheses there. That's an 8. It doesn't really look like an 8, but that's an 8. And then our total number was 4. There you go. And then it does the calculation for you here. So our variance for that sample is 22. Now remember, that is the squared deviations. So our scores aren't really on average 22 points apart. Clearly it's 1, 0, 6, 1. So if we want to know on average how far apart those scores are, we're going to have to do the next step, which is calculate standard deviation, which is, basically we're just going to take this 22 and take the square root of that. And that would give us the next step, which is standard deviation. All right, so now that you know sum of squares, and sum of squares is going to take some practice and just play around with it for a while, because we're going to keep using sum of squares and different variations of sum of squares for pretty much the rest of the semester. So just go ahead and spend some time sticking that in your head. Now remember, these are population formulas we've been working with. So we looked at calculating sum of squares and divided it by n. That gave us our variance, which was sigma squared. When we take the square root of that, we get standard deviation. Okay, so standard deviation is, in theory, simple. Okay, so that's that. All right, so I told you that populations are slightly different from samples. Here is the one and only thing that changes. Well, two and only things that change. One is the symbol we use to represent it. Now, we use Greek letters to represent populations. We use American letters to represent samples. Someday I'm going to look up and find out why. But that's what we do. So S squared now is the symbol for sample variance. And the only thing in the formula that has changed, because at the top, that is still sum of squares. Sigma x squared minus sigma x squared over n. That's still sum of squares. Was before, is now. Nothing changed. Nothing changed in how you calculate it, nothing. But look here on the bottom. On the bottom, we have this thing called n minus 1. In later chapters, that's going to be represented by this symbol, df, which stands for degrees of freedom. Which is going to be a big deal when we start looking at hypothesis testing and things like that. For now, I just want you to know that symbol exists. That's what it means. And n minus 1 is one of the ways we can calculate degrees of freedom. Now, it's going to get worse. I'm sorry. I wish I could be more hopeful, but it's going to get worse. That's okay. You guys can do this. And then here we have the symbol S for sample standard deviation, and it is just the square root of the sample variance again. So there's your sort of summary, and you've got your formula sheets as well. And that's kind of what we do. So let's just take a quick look at some of this really quickly. I told you that one of the problems with sample variability and sample standard deviation is the fact that we have to account for the fact that samples are much less variable than the populations they represent. So in other words, if I have a population of 1 million Canadian geese, I have no idea how many there are in the world. We're going to go with 1 million though. But I use only the Canadian geese that live in the pond behind DeSoto Center as my sample. Well, those Canadian geese, that group, they're going to have a lot more similarities than differences, particularly when I compare that group to all the differences of all the geese in all the world. So that creates a problem that we call a biased estimate of population variability. Because see, with these sample formulas, what we're really doing is trying to estimate what the population would look like, because we rarely actually have population data. So we want to use these samples to estimate that. And because those samples are biased, the estimate tends to be off. So to account for this, degrees of freedom, right, or n-1. Taking that one out, taking that one subject out, reduces the amount of bias that we have, right? And so that's why that formula is that way, all right? So that is sample. Now, as you're doing your homework and as you're doing your practice, one thing to be really careful of is making note in the question. Does it ask you about a population or does it ask you about a sample? Is it using population symbology or is it using sample symbology? Because that is going to change which formula you use, which is going to change your outcome. So if you want to avoid those simple mathematical errors, read your questions very carefully. So yeah, all right. So I mentioned, we're going to hit this again really quickly, that those notations are different for a reason. All right, population notation was Greek, right? Sigma squared. Ooh, I forgot to turn off my highlighter. That's okay. And sigma, that just makes it look fancy. Those were my population symbols because they actually represent the population variance and standard deviation. But we used American letters, S squared and S, to represent the answers from our sample because they actually represent estimates of the population by using a sample. All right. Most of the time, all we have is a sample to work with. So we're pretty much going to have to rely on that to give us an idea about what's going on. All right. So that's kind of the overview of variance. So we've got range, variance, standard deviation. We have calculations for populations, calculations for samples. All right. So just want to look at a few more things, just bits and pieces that are going to start to become important as we move forward. So I just want to introduce you to the idea. First off, this variance and standard deviation, these numbers are going to allow us to graph into that normal graph or that skewed graph when we sort of talked about these things, right? And those numbers are going to allow us to draw this graphic, this curvature representation of our data. And so what's going to happen is our mean, whether it's our population mean mu or our sample mean m, I have to turn that off, it's going to go in the middle. It's going to go in the middle whether it's a normal curve, and most of the time going forward, we're talking about standardized scores and so forth, we're going to be talking about a normal curve, so one that's symmetrical and that is the highest in the middle. That variance doesn't really give us any graphical information, but it allows us to calculate standard deviation, which is represented here. So standard deviation tells us how far we have to go down our curve to represent one average distance from the mean, which is what standard deviation is, the average distance from the mean. So if you have a score that is within one standard deviation of the mean of the middle, then your score is going to fall somewhere in here. Now there's a whole bunch of scores in there. But if we go even further, all right, and this was 88, all right, we had a standard deviation of 8, we have a mean of 80. Then between 80 and 88, all of those scores there we just listed. If we go another standard deviation, a second standard deviation, then we're going to add 16 to 80, right, which is going to be 96, or 88 plus 8, also 96. And this is how many scores fall in there, so fall far fewer. So as we start moving forward with this, what this standard deviation and mean and normal curve are going to allow us to do is to estimate the chances of getting a score in a certain range, or the likelihood that something is going to happen just by accident and by nature versus by some manipulation that we've put in. So it's going to start to become, it's going to kind of keep piling in on itself and adding more and more and more. So that's kind of a graphical idea of where we're going with this. When we change our data set, just like for mean, remember we said, when you add a score or subtract a score from the mean, if you multiply all the scores by a certain constant, if you divide by a certain constant, then that was going to change the mean. However, standard deviation is a little different. If we add that constant to each score, it will in fact change the mean, but it will not change the standard deviation. Why? Well, by adding the same number to every score, we haven't changed how spread apart the scores are. Instead, we've just changed where the middle of the scores are. So if I add 5 points to all of your tests, test 1, let's say you had an average, there it goes, you had an average of 80 on test 1. I like that. That works for me. And I add 5 points to that because I'm like, there was one question, maybe it was too hard, or maybe it was worded funny or something. That's going to change my mean to 85, but it's not going to change how spread apart your scores are. If your score was 10 points below the person sitting next to you, when I add 5 points to both of you, it's still 10 points below the person sitting next to you. If yours was 10 points above everybody else in the class, when I add 5 points, you're still 10 points above everybody in the class. The variability, and therefore the standard deviation, didn't change. We just shifted where our score, where our curve is located. So when we add, mean changes, standard deviation does not. All right, now, multiplication and division, a little different. It does the same thing to both of them. Remember, multiplying or dividing by a constant change the mean in the same way. It is also going to change the standard deviation in the same way. All right, so it causes the standard deviation to be changed in the same way. All right, so if we go back to, I don't know, let's do an example of a quiz where there are 10 questions. And you can get a 1, a 2, a 3, a 4, 5, 6, 7, 8, 9, 10. And let's say, I don't know, the world blows up and something's awful. And like the average score on that was a 2. Oh my God. I might look at that and just say, holy cow, I'm just going to like double everybody's score because something went bad wrong. So that's going to change where my mean is, right? It's going to change my mean to 4. but it's also going to change how spread out everything is. So if I had a standard deviation of 2, and so that's it. My scores went from 0 to 4. That's it. And I multiplied each score. Well, if you got a 2, the average score, it did change your score to 4. But if you had a 4, it changed your score to 16. Like it just, or no, it changed your score. We didn't square it. We multiplied by 2. Duh. It's going to change your score to 8. That's better. That's mathematically better. Did I mention that I make mistakes too? I hope I did, because I do. And so never be afraid to let me know if I've made a mistake, or don't be afraid of making mistakes. I get it. My point here was, though, my standard deviation now, so somehow we got to -2 here, I don't know, is 4. It is twice what the standard deviation was before. So when you multiply or when you divide, it's going to change both the mean and the standard deviation. When you add or subtract, it's just going to change the mean and not the standard deviation. All right, so using this stuff, y'all can read, I'll let you read kind of this, because as we get into the different kinds of scores and calculations and how we use them and so forth, you know, you're going to get to see that. We're going to work on things like z-scores and how you calculate standardized test scores like SATs and ACTs and MCATs and LSATs and PACS tests. If it's got letters and you fill in bubbles, it's a standardized test, and you're probably familiar with those. But we're going to look really at how we use that to describe your score. And then we're also going to look at how we can use these things in terms of inferential statistics. In other words, what does this really mean? What can we infer from that? You know, did our intervention, maybe our study group, our tutoring, did it work? Did it not work? Did it help or not help? So those are that's kind of where we're going with this in the end. So that is variability.